All right, so most of the time we spent talking about ideal gases. However, sometimes we do see non-ideal behavior, right? Gases don't behave exactly ideal. So again, most gases are close to ideal at standard conditions. So let's take a look at the kind of two things that break this ideal behavior. So if we think back to kinetic molecular theory, one of the things that we said that there's elastic collisions, right? The collisions are elastic. And so what that means is there's no attraction or repulsion between the molecules, right? That's what we said in our theory. In real life, that's not always true. There can actually be an attraction or a repulsion here. And so if this attraction or repulsion is strong, then the gas will behave less ideally. Later on, we'll learn about kind of what makes this attraction weak and strong when we learn about intermolecular forces. Then the other part of kinetic molecular theory is that we said that these molecules are of negligible size. Cool. And so that's true under standard conditions, but when we jack up the pressure a whole lot, then we push these molecules to get closer and closer together, right? And now they're really close together. So if you think about let me draw this even more exaggerated. If you try to compress this container anymore, try to increase the pressure, now the volume of these two gas molecules does matter, and you can't compress this anymore. And so as the molecules get closer together, because we're increasing pressure, size starts mattering. And our model kind of falls apart at these high temperatures because these gases do have size. And so one way you can kind of compensate for that is through this Z. Z is the compressibility factor. Compressibility factor, where basically this is equal to the volume of a real gas over the volume of an ideal gas. So it's basically you're taking kind of what the volume really is and dividing it by what it should be if it was ideal. And so if your gas is behaving ideally, then you'll get a value of 1. The further you are away from 1, the less ideal your gas is behaving. So here's kind of a picture of that. You can see on this left-hand side, plotted here, Z, and then here's pressure. And you can see these pressures are very high, right? 200-300 atmospheres, that's like 200-300 atmospheres pushing down on you. So at these kind of low pressure things, most gases behave quite ideally, but then you can see they kind of deviate away from this idealness. And the reason they deviate away from this idealness is because A, this attraction here, and then B, this volume here. So let's take a look at both of these. So we can write an even more complicated version of the ideal gas law, which takes these into account, this attraction and this volume, right? So you can see we transform this PV equals nRT into this more complicated version, but you still have P, you still have V, you still have nRT. We just add now corrections for this volume and this attraction. So you can see here that in this kind of part of the plot, Z is less than what would be expected, right? So our volume of our real gas is smaller than what would be expected. And that's because the molecules are attracted to one another. And so that's what this part is important for. At low pressure, you have to correct for the attraction of the molecules. And then when pressure gets really, really high, you start squeezing the molecules closer and closer together. And so now their volume matters. And so that's this part of the plot. And if you think about compressing something that has no volume, you could compress it infinitely, or something that does have volume, you can't. And so its volume will be greater than its ideal volume. And so you'll get a Z above 1. But basically just know that Z is the compressibility factor, how ideal your gas is behaving. Closer to 1 is better.